Hi everyone. In this video we're going to talk about the least squares problem, which states the following. Suppose we want to solve the equation ax equals b, but we have a little issue, namely that b is not an element of the column space of A. Yeah? So if B is not an element of the column space of A, what does that mean? It means that there are no solutions. Yeah? If we wanted to solve Ax equals B, but B is not in the column space, then X, we know, gives the coefficients for linear combinations of the columns of A. And if B is not in the column space, no such coefficients exist, so this means that this equation is not solvable. Yeah? So given that this is not a solvable equation, what can we do? We want to find the best solution. And by best, we mean best in the least squares sense, which we'll define. And this gives rise to the least squares problem. All right. Well, by best, we want the closest solution, yeah? So we really want to find some vector x hat such that the magnitude of A times x hat minus B is minimized. And I know what you're thinking. You're saying, boy, gee, howdy, this kind of looks familiar. If we had some vector B that didn't live in a subspace, how did we find a vector, in the other video I think we called it y hat or something, that minimized the distance between the two vectors? And that was a projection, an orthogonal projection, right? So let's do that. We will need an orthogonal projection. So the picture is the same as in the orthogonal projection video. Here is our subspace, but in the last video we called this W. Now it has a new name. The subspace will be called the column space of A, right? Outside of the column space, of course, is our vector B, yeah? Something like this. And we want to find, what's the closest vector? The closest vector, in the last video we called it B hat, right? That says B hat. But what do we know about B hat? We know that B hat lives in the column space. So that means that there are coefficients such that a linear combination of the columns of the matrix A with those coefficients will get you B hat. So that means that since B hat is in the column space, there will exist an x hat such that Ax hat is equal to B hat. Yeah? And what will B hat be? It's going to be the projection of the vector B onto the column space of A. Yeah? And because this must live in the column space of A, we therefore know that there must be a solution to Ax hat equals to B hat. But what does this mean for us? How can we make this something that's usable? We know that this vector, that dashed line vector, is the vector B perp, which we normally define as B minus B hat, right? That's our B perp vector. It lives in the perpendicular subspace. What do we know about B perp? We know that this B perp, which is B minus B hat, must be perpendicular to the column space of A. Well, what does this mean? It means that it's perpendicular to every column of A. It's perpendicular to every column of A. So, suppose A has columns A1 all the way through AN. What do we know, therefore, about b minus b hat dot a sub I? It has to be 0, right? If it's orthogonal to the column, then this dot product has to be 0. That's okay. Now, what is b hat? B hat is equal to a times x hat. So we get b minus a times x hat dot a sub I has to be 0, right? All right, so what do we want to do with this now? Rather than writing this as a dot product, we want to write this dot product as multiplication by a transpose. So we remember that we can identify this dot product as AI transpose times b minus ax hat. Yeah? And we know that this has to be 0 for every single value of I, right? This is true for every column of I. Any column that you pick between A1 through AN, this product here must be 0. So what do we know about the product? Let's write it here. A transpose times b minus ax hat. What do we know about this product? Well, each row of A transpose will be AI transpose, yeah? We know that all of these guys will be 0, so what will the result of this be? It will be the 0 vector, yeah? And this is kind of interesting here. Now we can distribute A transpose. We get that A transpose times B, I'm going to distribute and add it to the other side, must equal to A transpose times A x hat. Yeah? And this is a beautiful equation. This gives us a method by which we can find x hat, it turns out. This is called the normal equation. It's called the normal equation. And we notice that if we solve this, what is A transpose times B? This is a vector. And then if we compute A transpose times A and solve matrix times x hat equals vector using row reduction or whatever you like, we can then find x hat. And this is the solution to the least squares problem. Let's see how this works in practice. So, what do we know? So before we begin, let's just state what we know. We know that the set of least square solutions to the equation ax equals b coincides with the solution set of A transpose times A times x equals A transpose times B. And that's beautiful. That's easy peasy. Let's show why it's easy with an example. Find the least square solution to ax equals b if A is the matrix -1, 2, 2, -3, -1, 3, and B is the vector 4, 1, 2. Yeah? So, we could show that B is not in the column space, and it's not. So how would we solve the least square solution? So it's going to be the vector in the column space that is closest, in the Euclidean sense, to this vector, such that A times that vector is closest to this vector B. Okay? So what do we need to solve? We need to solve this equation. So we need to compute A transpose times A. Well, A transpose times A is equal to -1, 2, -1, 2, -3, 3. There's A transpose times A and whenever we do the multiplication, you should get the matrix 6, -11, -11, 22. Now let's compute A transpose times B. A transpose times B will be the matrix -1, 2, -1, 2, -3, 3, times the vector B, which is 4, 1, 2. And I think you get -4, 11. So what does this tell us? A transpose times A, which is this matrix, this 2 by 2 matrix, times some vector x must equal to this vector -4, 11. So what we know at this point is that if we solve the simple equation, easy equation, 6, -11, -11, 22, times x equals to -4, 11. Whatever the vector x is, or the solution set of x, will coincide with the least square solution. So this will give us the vectors such that A times those vectors is closest to this vector B, which does not live in the column space. How do you solve this? You do row reduction, and you should get that x is equal to the vector 3, 2. And this is the least square solution. Cool. All right. Let's state a little theorem before we do another example. Let A be m by n. Then the following are equivalent. Remember, so if one of these holds, all of them holds, and if one of them fails, all of them fail. 1. A transpose times A is invertible. Well, if A transpose times A is invertible, what does that mean? 2. That means that the normal equation has a unique solution. So AX equals B has a unique solution, a least square solution. For each B and Rn. That's an Rn, sorry. So AX equals B has a unique least square solution, and the content of the theorem here is that this happens only whenever the columns of A are linearly independent. Yeah? Ooh, independent. Spelling is hard. So in this case, what do we have? We have that our least square solution x hat, which is unique if we have linearly independent columns, must be equal to, well, where does it come from? We know that A transpose A times x hat equals to A transpose times B. How do we use this equation to solve for x hat? We're going to multiply it on the left by the inverse, given that this thing is invertible, right? So it'll equal to A transpose times A inverse times A transpose B. As an aside, the matrix A transpose A inverse A transpose is called a pseudo-inverse. It's called a pseudo-inverse. Yeah? And this allows us to get our least square solutions. All right. And of course, if A is invertible, then whenever you actually do this computation, it boils down to just A inverse. And you want to do that computation yourself if you don't see it. Show for yourself that if A is invertible, that the pseudo-inverse is the same as the inverse of A. Yeah. All right, but who cares? I know you're wondering, who cares? Let's do an example. Let's find the linear equation that best fits, in the least squares sense, the following data. Oops. 0, 1, 1, 1, 2, 2, 3, 2. So we have these 4 points, and let's plot them, just for fun. So here's 0, 1. Here is 1, 1. Here is 2, 2. Here is 3, 2. And we see that there is clearly no line that passes through all 4 points. So there's no interpolating linear equation such that all 4 points live on the same line. But what's the best that we can do? And we've seen this problem in all of our science courses, but I mean, would it maybe a horizontal line? Could it be a horizontal line? Kind of the worst of everything? Maybe something that's kind of slanty here, but where exactly should it go? And how do we know that it's the closest? Yeah? So how do we formulate this as a least squares problem? Well, our desire in this problem is to make it a linear equation. So we want our equation to look like y equals mx plus b. And we know that all 4 points will not be satisfied here, but suppose they were, right? Well, let's plug in this value of x and this value of y. Then we will get 1 equals to m times 0 plus b. Plugging in the next set of points, we get 1 equals to m times 1 plus b. For the next value of points, or the next set of points, we get 2 equals to m times 2 plus b. And for the fourth pair, we see that we have 2 equals to m times 3 plus b. Yeah? What do we want to find here? We want to find m and b that best fit these equations. So how would we solve for m and b? I see 4 equations and 2 unknowns. You might be tempted to take the coefficients here, which are 0, 1, 2, 3, 1, 1, 1, 1, augment our solution vector here is 1, 1, 2, 2. But you'll quickly find out that this has no solution. So indeed, we cannot find a single line that exactly passes through all of these 4 points, but we want to find the best solution. So how can we do this? Well, let's call this matrix A. Let's call this vector B. And let's solve the least squares problem with A and B. So at this point, you should pause the video. Try to solve this problem yourself. All right, so I think that A transpose times A should give you the vector, or the matrix, 14, 6, 6, 4. The product A transpose times B should give you 11, 6. And now you want to solve the equation 14, 6, 6, 4 times some vector x, hat we'll call it, equals to 11, 6. Yeah? Whenever you do this, I think you should get that the vector x hat is equal to the vector 0.4 and 0.9. Yeah? Whenever you solve this equation, either with row reduction or multiplying both sides on the left by A inverse here. Either one works. But for larger equations, the row reduction is certainly easier. So what does this mean? What's this vector x hat? This is the best solution. The first entry corresponds to the values in this column. And what were the values in this column? Those were m. The second entry, 0.9, corresponds to this column in our matrix, which is the value for b. So this means that the line of best fit is the equation y equals 0.4x plus 0.9. And that's kind of cool. So, I know what you're thinking. How do we make sure that this equation that we find actually matches what we use in our calculators, right? And Excel should all give you the same answer. Let's verify that, right? So, every time that you've seen this, your calculator is not performing some magic. It's solving the least squares problem. So it's actually solving the system of equations. So all that I've done, I've put in my calculator the set of points. Here they are. 0, 1, 1, 1, 2, 2, 3, 2, and I put those in my entries here. And how do we find the line of best fit if we were in pre-calc or something? We go to Stat, go over to Calc, and we compute the linear regression. My x values are in the L1 list, the y values are in the L2 list. And if we calculate the linear regression here, we see that we get 0.4 and 0.9. So your calculator, Excel, is all doing this. This is the magic behind the scenes. It's not magic at all, it's mathematics. So I hope that this helps, guys. If you have any questions, please don't hesitate to reach out. I'm happy to help in any way that I can, or we can set up a time to Zoom. And I thank you all for watching, and I look forward to seeing you in the next video.